Welcome to the Engineering Room, a monthly series of long-form conversations with influential people from the software world. The Engineering Room series is sponsored by Equal Experts, and I'd like to thank them for their ongoing support. So if you'd like some help building some great software or are interested in finding a great place to work, do check their links out in the description below. I first heard about the work of our guest today as a result of his best-selling book, Your Code as a Crime Scene. You have to admit that's a fantastic, intriguing title for a book. He's a programmer with an interesting academic background too, holding degrees in engineering and in psychology. He's a founder of CodeScene, where he designs tools for code analysis. He's also the author of multiple technical books and a speaker on the international conference circuit. Please welcome our guest for today, Adam Tornhill. Welcome, Adam.
Thank you very much, Dave. Great to be here.
I'm looking forward to our conversation. As I said, I was always intrigued by the title initially of your book, Code as a Crime Scene, and then some of the ideas in it. And I saw you recently, not very long ago, end of last year actually, speaking at a conference where you were talking about some of this in more detail, which kind of reminded me of what an interesting topic this is. So can you explain a little bit what you mean by treating your code like a crime scene?
Yeah, sure. I'll be happy to do that. And I have to start and travel a little bit back in time because, you know, when I started to work professionally as a programmer, I already had some programming experience. But I still kind of found that once I joined these larger companies, I found that software development at scale is a very, very different thing compared to what I had been doing before, right? Yeah. And in particular, I found it was really, really hard to reason about large code bases. So that's when I decided to kind of go into psychology. And my plan originally was just to do like an introductory course because I kind of thought that psychology should have a lot to offer to us as engineers, because psychology is very much about how we think, reason, and solve problems. And it turns out that psychology is really, really fun. So I plan to spend 1 year there, but I actually spent 6 years at the university and eventually took my master's degree, right? And at the same time, I was kind of fortunate to work as a software developer. So that gave me so many opportunities to take what I learned in psychology and kind of, you know, apply it to my day job. And Code as a Crime Scene kind of came from that intersection. So at that point in time, I did some work for a company, and they were really, really struggling with the software delivery. They were really, really slow. And there was a huge pressure of delivering stuff quicker. And somehow it turned out to be like my responsibility because I was hired as the technical leader on that project. And I found it really hard to do. So I tried a bunch of these traditional approaches like static analysis tools, tried to identify the worst bottleneck, looked at the value streams and that kind of stuff. But I kind of found that it was so hard to communicate around something as deeply technical as code. So at the same time, I was in the middle of my psychology studies and I took this course in forensic psychology and learned about something really, really fascinating called geographical offender profiling. So I'm not sure, have you heard about that, Dave, before?
I have. I watched a documentary about it a few years ago. It's an interesting topic. So the thing that I was seeing, if I'm remembering this correctly and talking about the same thing, these people were using geographic profiling of crimes in order to be able to predict where crimes might occur.
Yeah, exactly. So they, what you do is basically that you consider each crime scene, its geographical location, as a center of gravity, because you know there has to be an overlap in time and space between offender and a victim, right? So the crime scenes carry information, and then you simply weight them together mathematically and project that on a map, and now you get what offender profiles call a hotspot, right? And that's the area with the largest probability that the offender will have their home base there. And when I learned about this stuff, I was just like, wow, what if we could do the same thing for software, right? What if I could pick up these large code bases I'm struggling with and kind of, you know, get a probability surface on them and know that if I focus our efforts to the hotspots, then we're very likely to get the real business benefit, you know, being able to ship quicker, better quality. So that's where it kind of started.
And I've seen you talk about this recently, and now you talk about those hotspots as red code and areas that are interesting to focus more attention on and so on. Was that something that you came to immediately, that idea of code health, or was that something that you, and being able to highlight it visually, or was that something that, I don't know, you iterated over and came to more slowly, but it was just the core idea of the geographical analysis that started off?
So code health actually came much later. So I started to do this work like maybe 12, 13 years ago with the hotspots, and I found it super useful. And I put a lot of effort into how can we visualize these hotspots? How can we build maps over the software, right, where you see the hotspots?
Yeah.
The idea here was that we just use that to kind of simplify our communication, right? And use the hotspots to help us focus our attention to where it's likely to be needed the most.
Cool. So sorry, I interrupted.
Yeah, no, sorry, please go ahead.
I was just intrigued about, so where did you start off in trying to differentiate? If code health came later, where did you start with trying to identify the hotspots?
So what I did with the hotspot was that I based in the first iterations, I based them purely on behavioral data of how we as developers interact with the code we're building. And that turns out that's data we all already have, right? We just don't think about it that way. It's in our version control data, right? So the first version of this was purely language neutral. You could use it for any programming language as long as it was text-based and under version control, right? So that really, really helped, because I found that no matter what system you look at, the development activity is very unevenly distributed. There's always a very small part of the code base, maybe just 1-2%, where most of the development activity is. So my thought was that if we focus on that part, then we can inspect that for code quality issues, technical debt, all that stuff, and be pretty certain that if we pay that down, then we're going to get a real benefit. So that was the first iteration of it. Then what I ran into later, a couple of years later, when I started to do, before I built a product around this, I used to do services. So I went to clients and I helped them out with like mapping up their system, profiling them. And what I found was that I had to spend a lot of time explaining why a particular piece of code is a problem. And this was time consuming for me as well, right? I had to pick up the code, I had to review it. And I actually started to think, isn't there a way to do this automatically? So that's what kind of code health grew out from. I basically started to formalize the things I used to do manually when reviewing code and see, can we write code analysis tools that detect these various code smells and kind of combine them together and give me this snapshot.
So that sounds a bit like two different things to me. So I might be misunderstanding. So the first part where you started sounded a little bit like traffic analysis. Is the old code breakers used to, they couldn't break the code, but they could learn a lot just by analyzing how the flow of communication. So you're kind of looking at the traffic analysis through analyzing, the commit history essentially. But then you're adding on the sorts of metrics for the health of the code as well. Is that correct?
Yes, that's correct. So it's basically two different perspectives that we need to combine if we ever want to manage tech debt. And the reason I say this is because if you look at traditional static analysis, I mean, that's where I started, right? The main problem with that is that it completely lacks context, right? Yeah. So I might put it on an existing code base and I end up with like 5,000 major findings, and there's no clear priority between these findings, right? But you still need to have that quality perspective. We need to separate the good from the bad code, right? But then we need another perspective, the relevance perspective, and this is what I think hotspots offer.
So I'm just trying to tease out the detail of the meaning of this for my own understanding. So the traffic, the static code analysis approach, tells you this piece of code is a problem, but that doesn't mean that that's a sensible piece of code to work on. It might be working and nobody's touched it for years, and it doesn't matter that it's a problem because it works.
Exactly. that's a very good summary. So what I'm saying is basically that just because a piece of code lacks in quality, that doesn't mean it's an immediate problem, right?
Yeah.
Something you probably want to know about, but yeah.
I remember reading some analysis years and years ago. I think somebody was trying out some code analysis tools against it might have been the Unix code base rather than the Linux code base then. But there was this one bit that didn't fit because they were looking at this, and they were doing something similar to what you're doing, but not as sophisticated, I think. But there was this one bit that had huge cyclomatic complexity. It was a really nasty piece of code, but nobody ever touched it. And that was because everybody was scared and it worked. So nobody touched it.
Yeah, I think that's a pretty common finding, right? But then you have the other type of problematic code, right? The code might really objectively be a mess, right? But maybe it's a stable mess that's been debugged into functionality, a stable part of the domain. I mean, why spend time fixing that when it doesn't need to be fixed?
Yes. So the second part of your approach kind of highlights the value of changing this bit that's problematic.
Yes, that's correct.
And that's when we get to the red code, right?
That's how we get to red code. So to kind of simplify the presentation a bit, because what I'm working on, one of my main goals is to help us as developers and engineers to have conversations with the business people that might not necessarily know how to code, right? I want us to have a common language. So what we do with this code health metric, it's fairly granular metric, but what we do for presentation purposes is that we classify every single piece of code as being either green, which is good, healthy code that we can easily understand, versus the red code, which we know is rich on accidental complexity, is really, really, it's a large risk to modify it. So that's where the red code concept comes from.
Cool. So how do you measure that aspect? Is that using similar kind of traditional techniques to static analysis, or is that stuff that you've developed yourself as well as a model for what code health is?
So it's something we've developed ourselves, but we stand on some pretty gigantic shoulders, because we try to base all the stuff we do on, and that's always been my approach to base it as much as possible on existing research, right? Because I kind of want to make sure that the things we recommend to people, that it's likely that it actually works. So what I did was I spent a lot of time kind of digging through research over the years and figuring out which type of code smells and coding issues really impact our ability to understand a piece of code, because I think that's the main constraint. Main time constraint, right? That's our ability to understand code. How long does it take us to build a mental model of a piece of code? So I identified like 20-25 factors that make code hard to understand. So what the code health metric does, it sticks these 25 probes into each piece of code, pulls them out and see, okay, what did we find here? And then our main contribution is that we have an algorithm that can kind of weight it together and do this classification into green and red code.
Right. So could you just give us an example or two of the kinds of measures that you would use to verify the health of the code?
Yeah, I'd be happy to. So in general, we do this detection at 3 different levels: the module level, class level, function level, and then implementation level. And at the module level, you have classic things like low cohesion, right? The module does too many things. You've stuffed too many business responsibility into it. Yeah. And that's a problem, because it's, of course, hard to understand the code, because you need to understand all these different concepts. And it also kind of puts you at risk for things like unexpected feature interactions, which are some of the most nasty bugs you can have.
So what sorts of techniques do you use to measure poor cohesion?
So we use a version of, there is this, it's a pretty standardized metric. It's called outcome 4, which I think stands for lack of cohesion metric. And 4 simply indicates that this is a really, really hard problem. So it's like the 4th iteration of it. Yeah. So we have an adapted version of that we use.
Cool.
Yeah. the way it works under the hood is simply that you try to identify, given a set of functions inside a class, you try to identify various subgraphs, like, okay, these functions seem to belong together. They're modeling the same concept. Perhaps they call each other, perhaps they use the same data. And then you really want everything to kind of solve the same problem and belong together.
Yeah. So yeah, that when you mentioned that, when my head started going down there, I was thinking of trying to identify the behavioral interaction with different bits of data, and I could imagine you being, little localized parts of a nasty piece of code, being all over the map with that kind of thing. But good code looking neat and tidy. Yeah, makes sense. So you're doing these variety of different measures of the health of the code. One of the things that you said kind of intrigued me, because one of the ideas, it's at a much simpler level in terms of code quality than what you're talking about. But one of the ideas that I've been pushing, if I'm honest, recently, is the idea that it seems to me that the most important measure of quality of our code is our ability to change it. And not much else matters. And so the other parts of that ideas like cohesion, matter because they maintain our ability to change the code easily. Do you think that's a reasonable kind of overview picture of what we should value as quality in code? Or do you think there's more to it than that?
I mean, it's hard for me to disagree with that statement, because I think it's right that our ability to change a piece of code is a super important driver, right, for code quality in general. I think there might be a bit more to it, because there is this wonderful book by Robert Glass called Facts and Fallacies of Software Engineering, an old book, but still one of my favorites. And he kind of has this 60-60 rule that I've been referring to over the years, where it says that 60% of your work is making modifications to existing code. And 60% of that time, in turn, is spent trying to understand what the code does in the first place.
Yeah.
So that kind of enforces your point that, the ability to change is important, but I also think that the way you optimize for change is by making the code as easy to understand as possible, because that's where we spend most of our time. So to me, we want to optimize any aspect of code. We should optimize for ease of understanding. That's where the big win is.
I certainly wouldn't disagree with that. I guess the analysis that I make is that the reason why ease of understanding matters is because it makes it easy to change the code. It's not that but ease of understanding is absolutely one of the most important tools that we have at our disposal. I was just intrigued. I suppose in part I was looking to see if you reinforce my opinions or helped me to reinforce my opinions. But I just think it's an important idea, because I think often we get hung up. I think the technicalities are important, but we need to understand why the technicalities matter. Why is it that poorly cohesive code is worse than nicely cohesive code? And it's for these kinds of reasons, and so it helps me to understand and think about and prioritize the kinds of changes that I was making. So sorry, I'm just going off on one of my hobby horses now, but I think it's an important idea, and it's certainly one of the ones that I am trying to popularize at the moment, I suppose.
Yeah, I absolutely agree. And one of the barriers related to that I've been trying to tackle over the past years with the research we have been doing, that has been to try to make code quality relevant at the business level, because yes. I think that's something that's very much undervalued at the moment.
And that was one of the things that I really loved about you. I don't know whether it's your current conference presentation, but the one that I saw at YOW at the end of last year, it was one of the things that I really liked about it, because you're putting this in the real world. This isn't, we can talk about, ideas like cyclomatic complexity and all those sorts of things, on the technical front, but that's meaningless to somebody without a translator. And so putting this into the context of real value, the real value to organizations that practice software development of being able to use software development capability in the commercial interests or whatever other interests of the company that's engaging in it. It's so important. We're not, as professionals, we're not doing this for some purist ideology or whatever of nice code. We're doing this for practical reasons because we get to make more software more easily if we make our code high quality. So I think it's a really deeply important problem. Yeah, so your stuff just brings that alive. The demonstrations that I've seen of the product's called CodeScene as well as your business, I think, isn't it?
Yeah, that's correct. That's the name of both the company and the tool.
Yeah, so the CodeScene product, it does kind of bring it alive, so that you can show those pictures to anybody, whatever their technical background, and have a sensible conversation about them.
Yeah, and I think that's a super important conversation to have inside any organization, right? Because one of the challenges I've seen myself over the years is that I had so many people telling me that, no, we cannot afford to do this, right? We don't have time to rethink the architecture, don't have time to automate tests, don't have time to refactor, right? So somehow there is this, I would like to say it's a perceived misconception that there is some kind of trade-off between speed and quality, right? We can either go very fast, we can go well, but it will slow us down. And the data we have been collecting and the research we have been doing, and I think this is very much supported and in alignment with the DORA research, right? That
yes,
there really is no such trade-off. I mean, the opposite is true, right? We see that the companies that manage to move with high quality, they also can deliver in much shorter development cycles, can ship much, much more. So there is no such trade-off.
Yeah, and I was delighted when Dora first showed that, and your work reinforces that message too, because subjectively that's always been my opinion, is that the reason why quality matters in code is because it allows us to build more software. It allows us to it allows us to go faster fundamentally. From a commercial point of view, once again, this ought to matter to every software development organization, because it seems obvious. It seems very obvious, I suppose, with the benefit of hindsight, and it's really nice to have this more scientific backing of studies like yours and the DORA measures. But it seems fairly obvious that if you build crap software this week, you're going to go slower next week because you're fixing all the problems that you introduced last week. It's just crazy. So it's certainly been my own subjective experience that the best teams that I've worked on not only built the best software, but also went a lot faster than other teams. There just doesn't seem to be a distinction between those. And I think that's just one of those myths that surrounds our industry. And we've kind of built up structures and project management disciplines and all kinds of things around that mythology. It's a problem.
Yeah, I agree. I think it's a very destructive myth. And I think part of the problem is that software is a very abstract thing, right? It lacks visibility. Yeah. And I think the consequence of that is that doing improvements to the internal quality of code, like larger refactoring, that kind of stuff, it kind of lacks on external value, right? The software is doing the same thing, which is the purpose of refactoring, right? But there's nothing I can sell to a client. It's not doing more, right? It doesn't have more capabilities. And that always means that improvements tend to get the backseat compared to adding the next big feature, right? So it's a hard sell, larger improvements.
Yeah, and people, I think we're all kind of products of an industrial civilization. We grew up with people building cars or widgets or whatever on production lines, and so we have that kind of manufacturing meme planted deeply in our psyche. But software development is not about manufacturing in the slightest aspect. It's a very, very, very different kind of thing, and manufacturing techniques don't work. So you know, I think it's interesting. Well, let's get back on topic of the things that we're talking about, your stuff, rather than me just philosophizing for a minute. But I one of the things that you said early on about when you decided that you wanted to start off studying psychology was that you thought that might give you insight. I found that interesting, and one of the things that I don't know if I can pull this out very easily, but there seems to be a link there with that idea and your very visual approach in terms of presenting the information in a consumable way. I've always had a very strong appeal to strong visualization of information. And I think deeply that's what your software does, is it's got a very strong, straightforward but strong visual impact when you see it being used. Can you describe that a little bit more, and maybe, you know, sort of just tell us a little bit about some of the things that you've been able to see that are unexpected from that kind, using those kinds of visualization techniques?
Yeah, that's right. So CodeScene and my work in general is very heavy on visualizations, and that's because the human brain, in particular the visual part of it, is really the most powerful pattern detector we have in the known universe, right? And it kind of still amazes me. I've been using these techniques for a decade now, but it still amazes me how quickly I can get insights into a code base. So just to give you an example, just yesterday I had a look at a new code base. It's like roughly 500,000 lines of code, so I would say a mid-sized code base. And I know that if I would try to approach this from just the code, it would probably take me months before I was even vaguely familiar with that system. Mm-hmm. What I do now is I put it through CodeScene. I look at visualization. So CodeScene visualizes it like a map. I can see the folder structure. I can see the various files visualized. And then we use color to kind of highlight the things that I need to focus my attention on. So in less than a minute, of course, I'm fairly used to reading these visualizations, right? But in less than a minute, I can immediately tell if this code base has technical debt or not, if it's a major concern. And I can also tell in what direction that's moving. Is the system getting better or worse over time? So, and that's really just for the start of it. That's the technical side of it. And there's a whole set of visualizations to uncover, like what I call the social side of code, but that's a slightly different topic.
Mm-hmm. So you get this visualization, and then what comes next? So that's going to highlight areas that we can most profitably work on.
Yeah, it's going either to tell you that, okay, yeah, everything is okay here, just keep up the good, and that's actually a very rare outcome, right? But it happens every now and then. Some people doing an excellent job on these aspects. But what it will do otherwise, it will tell you that yes, you have some severe code quality problems. It will tell you exactly where they are. It will tell you what they are, and it will also tell you what you should do about it. And the most important thing is that all of these issues are then prioritized based on how you actually work with the code. So like we talked about earlier in this conversation, if you have a piece of code that lacks in quality, but it's a stable part of the code, then CodeScene is going to tell you about it, because it's important to know about these potential long-term risks. If you have a plan to do something here, you should know about this, right? But it will also tell you that, okay, these are the parts of the code. You might have less severe problems here objectively, but these parts have a higher interest because you work on those parts all the time. So It's going to give you like a prioritized list. That's basically a starting point.
So in one of your talks, I think I saw you talking about this aspect as prioritizing technical debt and using something called Lehman's law to manage this. Could you just dig into that a little bit more deeply and explain that to us?
Yeah, sure. So Lehman's laws of software evolution. It's a super interesting paper, and there are two laws there in particular that I tend to refer to because they kind of capture the essence of software development to me. And the first law is the law of continuing change, which claims that a software system will have to be changed and modified. Otherwise, it will become less attractive and less useful over time, right? And
Yeah.
I think we have all seen that, right? None of us has an empty backlog. So successful software will evolve. But that's in stark contrast to the second law of software evolution, which is the law of increasing complexity. And this law says that when our system evolves, its complexity will increase unless we very actively work to reduce it. Mm-hmm. And there is, of course, a conflict between these two laws, because if I'm allow the complexity to just increase, it's going to be even harder to respond to change, right? So this is a really, really vicious circle that I see a lot of companies end up in.
Yeah, and you end up. We even have words for these systems: big balls of mud, legacy systems, those sorts of things. We end up in those unpleasant positions. So the visualization of the hotspots gives us a route out by focusing our attention on the technical debt that's more profitable for us to pay back. Is that a reasonable summary?
That's a reasonable summary. And what you then do is that you can actually, you can either use that to kind of focus your work and start to act upon that, or you can even, using the data I talked about earlier, you can even, if you need to, you can even build a business case for that improvement, right? Because there will be a business benefit. If you take some red code, make it green, you can actually estimate how many fewer defects you're going to have, how much quicker you're going to be able to iterate on that part of the code. And that's something I personally find interesting.
So how do you identify the nature of the costs that you're incurring? In order to make that kind of case, presumably you've got to be able to point to and say, this is costing you X because of, this property of the code or this bit of red code here. How do you start to paint that picture?
So we have like a statistical model that kind of came out of our research, where we know that, if you have red code, on average, it's going to take you twice as long to implement something in that code. We also know that the risk it will take 10 times longer is pretty high, right? There's a huge uncertainty, which makes it really hard to kind of guesstimate those part of the code. And we also know that red code on average has 15 times more defects, right? So we can use that same model to kind of reason about this backwards. If I manage to take a piece of red code, I refactor it and make it green, then I would expect to be twice as quick for all the stuff I have planned in my roadmap that touches that area. I would be able to reduce the uncertainty in my estimates, and I would definitely have fewer defects. And this is something that you can actually measure and visualize and see that it actually happens.
Cool. And is that model built on your analysis of code bases and organizations, or do you do other research beyond that in order to build this model?
So it's basically based on the data we collected via CodeScene, because we have these metrics built into the tool, right? So we're kind of using it to collect the research data too. But what we did was that we basically opened it up for lots of organizations. So we had can't remember how many, but we had hundreds of different code bases, including that baselining data. So what we did was that we collected information about the code health of every single module. We also collected data by hooking into tools like Jira and Azure DevOps, right? We could kind of calculate, okay, what's your development time? What's the time in development for each task? And since we had Jira, we also knew, is this a new feature or is it a bug fix, right? Which made it possible to build this model for defect densities. So the data behind this statistical model comes from real-world proprietary software development from all kinds of industries and programming languages. So it's like a very general model.
Cool. And so now you've got this, as you said, a predictive model that you can kind of use to back up those conversations that you were talking about.
Yeah.
Sorry, I interrupted you. Go ahead.
No, I just want to say that this is something, this line of research is like a little bit of a personal dream. This is exactly the type of data I would have benefited from a lot 10 years ago, back in my days as a consultant.
Yes.
Because I was so often at the losing end of these conversations, right? I was pushing for, hey, we really need to improve this, right?
Yeah.
It's a complete mess. And I kind of always lost those arguments because I couldn't really prove anything, right? And I couldn't bring up my static code analysis data because, the moment I mentioned something like cyclomatic complexity to a product manager, they're never, ever going to talk to me again, right? So it's, I really wish I had this back in the day.
Yeah. One of the other ideas that I heard you talk about was internal versus external quality. Could you just explain that a little bit to us and how that plays into it?
Yeah, so I think that the distinction between internal quality and external quality. So external quality is pretty easy. So that's like, okay, how many bugs do we ship in production, basically, right? It's very much related to the product maturity experience. And the internal quality, that's more like, it's more like the root cause of the external quality, right? So internal quality is something that's not directly visible to a customer, but it could be things like low code health, an unhealthy system, that kind of stuff that is going to impact us as engineers working on that code.
So the external qualities that, as it sounds, the stuff that users are going to notice it falls over, or they suffer from a bug and lose some functional or some money or something like that. And the internal quality is really the causes that sometimes the causes of those failures, but might be more broad, like it just makes this code harder to work on.
Yeah, but there is, of course, a connection between them, because
I
have, if I have unhealthy code, right, I have low internal quality, I'm going to ship a lot of bugs into production. So not only am I going to get unhappy users, the main problem is that all these bugs, just like in the Stephen King movie, they're going to come back, and they're going to come back as unplanned work.
Yeah.
And unplanned work, I love this phrase. I know Jim Kim used it in, I think, the Phoenix project, right? Unplanned work is the silent killer of IT projects. And it really, really is, because it's going to consume all your time. It's going to be ad hoc, lots of context switches, and you're going to have even less time to pay down tech debt or improve code. Yes. So it's really, really dangerous.
And that's the reason why we go slower when we build lower quality systems. Yeah.
It's a self-enforcing feedback loop, basically.
Yeah. So you talk a lot about technical debt, and some people don't like the model. I'm never quite sure that I understand the arguments against it. It seems such a useful concept to me on the whole. Where do you stand? Is technical debt wholly a good model for approaching these kinds of problems, or do we have to be cautious around it? Are there ways in which we can accidentally misuse it and misinterpret what it means, or misread the signals, do you think?
So I personally find that it's still a useful metaphor, and I'm using it quite a lot. What I think is that quite often we're misusing technical debt to mean any bad code or any problem in general, right? That's not necessarily technical debt. So, but what I like about technical debt is this interest component, and this is something that we might not be discussing enough, because to me that's like the central part of it, right? You can have technical debt, but it's basically a free loan because you never work on that part again. Yeah. Or you can have technical debt in a hotspot, which is the equivalent of, I would say, an SMS loan or something, right? It's a ridiculous interest rate on that.
Yeah.
So I find it useful.
And so, what are the traps then? So the traps are not to think in terms of the. So I think it always seems to me that if you do align the idea of technical debt with financial debt, that teaches you quite a lot. So sometimes financial debt's a good idea, and you can use it as a tool to do things that you couldn't otherwise afford to do. Other times it's a terrible idea when you're, paying off your gambling debts with your credit card or whatever else. It's a bad situation to end up in. And I see analogues for all of those kinds of things in people talking about technical debt and using technical debt or suffering from technical debt in their code bases. But in the conversations, I've had people say to me, as a consultant, don't talk to the product owners about technical debt; they'll just turn off. So there's something that's not landing with that as a model sometimes, and I just wondered whether you thought about that, or you had any advice on how best to present these kinds of ideas. Your visualizations help, I think. But I just wondered whether there were any other ideas around technical debt that might pay off. And sometimes it's just the scale, because like everything else in software, the scale at which these things can happen. I think I might be quoting you back to yourself again. I've got in my notes here something about staying on top of 4,000 years of technical debt. It's really easy to imagine organizations that get into the equivalent of those sorts of situations if they don't act to manage their debt and control it seems.
Yeah. And I kind of think that there are, technical debt, I kind of, like I said, I like the metaphor, but I think that terminology might be a little bit tricky. So I think a couple of things happen. The first is that it contains the word technical, which immediately signals that this is something we should care about, engineers, right? Let's push this down to the engineering department. And I don't think that's good. I don't think it's good enough by any means, because technical debt is a business problem, right? If you have it, then you need to care about it. Yeah. And my experience is I'm fortunate. I get to meet a lot of C-level executives, and most of them are aware of technical debt, right? So the awareness is there. They're aware of the consequences. However, the big problem is that we have somehow gotten comfortable to just accept that we might have technical debt. We don't know at what level. We don't know where it is. We just live with it. And I think that's the thing I would like to change, because I think as a business executive, you should know exactly what level of technical debt you have. You should know where you have it, because it's going to constrain what you can do as a company with your product. So I think that's part of the problem. The other is that we have, like I said, been misusing it, right? So in the same sense that we're, as a community, might misuse a term like refactoring, right, to mean changing code in general, which isn't, right? It's quite a structured process. So I think it's a little bit the same thing with technical debt. We, maybe we implemented some crappy solution, now we call it technical debt, and we want to fix it, and maybe it is, maybe it isn't, right? But technical debt, like you said, to me, it's also a tool. I'm not religious about code quality by any means, right? So I occasionally myself write code that I'm not super proud of. And the reason I do this is because I have the additional benefit of context, right? So I know that this is a code in the long tail, right? This is code that's very far from a hotspot, right? And maybe I need to fix a bug there, right? So I do that fix, and I might squeeze it in. I might add to the complexity. I put in those extra if statements, right? Because it's a safe bet that I will never have to look at that code again. So
thank you. Let's move on a little bit. So we were talking earlier about the kind of measures of code health, and I was going to throw some words out at you and see. And again, I'm quoting you back at you. That and if you've got anything to add to these, I'm particularly interested in. You talked about brain classes and brain methods as problematic in code. What's a brain class and a brain method?
So let's start with the brain class. So we spoke about low cohesion earlier. Low cohesion is a massive problem, and that doesn't mean we cannot make it worse, right? So we can take a class with low cohesion. We can make it really, really large by adding many lines of code to it, right? And we can make sure it contains at least one brain method. And a brain method is like a function level smell that, and we have probably all seen them, right? It's these methods that are really, really long. They're always long. They contain a lot of complex logic. and they kind of tend to centralize the behavior of the class, right? So each time you make a modification to that class, you end up in the brain method, and over time they just become more and more complicated. So that's a brain method, also known as a GAD function.
Yeah, I can remember a very, very long time ago. I think on my first professional C++ project, a very long time ago, somebody came up with the idea of a God class and saying, this is brilliant because it can create any other class. And really? but we thought it was kind of probably an okay idea then. I thought it was just badly named. But yeah, these things get very messy very quickly, it seems to me. So I have had a pushback occasionally when talking about some of these design ideas, and certainly my style of code is many small pieces. So usually you can tell what the bit on the screen is doing without reading any further, because it's concise and it's just a few lines and it's very simple. Mostly that's the case. Occasionally I might incur some debt like you for some tactical reasons, but usually that's what my code looks like. And one of the criticisms that I've had of that style of code is that it's got such a big surface area. But I was talking to Michael Feathers about this, and he said something that I liked, which was that's just the surface area of the problem, that the code should be representing the problem so that you can see the problem in small pieces individually. Sometimes there are some people that will argue that these things like brain classes and brain methods are easier to understand. I think they're crazy, but so I've had that mentioned because they can see everything in one place, whereas they've got to go and look in another file to see another class or another module or something like that. But I think that seems to be one of those tools that we use to decompose the problem into pieces that are immediately consumable. Going back to what you said at the start or much earlier on, which is we want our code to be almost instantly readable. We'd like people to read it. Oh yeah, I know what that's doing.
Yeah, I'm very much on your side here, because I think that if we consider something like a brain class or brain method, right, I like to think that those code smells, they are really just symptoms, and the root cause is a complete lack of modularity and a complete lack of encapsulation. Yeah. And so I think that, and this is something where I also get the pushback every now and then when I suggest a refactoring, because I do workshops every now and then. I kind of love to refactor code, right? So let's say you have this large method, and I suggest that, it's actually doing 3 different things. So let's kind of take each one of its responsibilities, break it into a method and put a name on it. And, at the surface, it's the same number of lines of code. We kind of just sliced it differently, but cognitively, it's a massive difference, because the moment you put a name on something, it turns it into a chunk, something that you can reason about, right? Something you can fit in your head. So it's not the same code.
Absolutely. I think it's one of those other, to me, key ideas that somehow some people seem nervous of in coding when having these kinds of conversations is abstraction. When you're talking about, the difference between your 2 examples is that they were abstracted differently. You abstracted out the 3 different parts of the problem, and then you name them, and you can more clearly see where those interactions are and so on. And that's another area that I sometimes get pushed back on, is that abstraction is bad because all abstractions are leaky. But that seems a very odd thing to say to me, because it seems to me that software is almost everything is almost entirely about abstraction. Driving a car is about abstraction, let alone writing software. So it seems to me these kind of fundamentals are fundamental. They're tools that we should be using to be able to avoid some of these patterns that you're talking about.
Yeah, and I also think one reason is because if we have some really, really complex code, and that code is hard to understand, then we like to think that the solution has to be complicated too, right?
Yeah.
And I think there is so much value in these super basic refactorings like extract function. I use them all the time. And
Yes.
what I find is that, the moment I extract a couple of functions and put some effort into naming them, it kind of tends to suggest the next refactoring step, right?
Yes.
So it's a reasoning tool, basically.
Yes, yes, and often as I'm going through that process of refactoring code, I'll hit moments of insight. Oh, now I know what's going on here, and that might change the direction of what you're going. But it's a way of learning about the code as well as reshaping it for the better. It's one of the ways in which I explore code bases that I don't know very well is by going in and starting to refactor them, because that helps me to understand them better.
Yeah, definitely. It's a powerful tool. And I kind of learned that, when I went into psychology to kind of understand why it's so hard to write code. One of the first things that surprised me is that we're actually capable of writing any code at all, because it just shouldn't be possible, right? The human brain is actually way too limited. We have all these cognitive bottlenecks.
Yes.
And I think that good code is code that kind of managed to work around those bottlenecks, right? Rather than take them on head on, like, for example, a brain method does, right?
Yes. So I don't know whether this is an unfair question, but could you point to what you think the secrets are of maintainable code? I suppose you must be able to, because you're measuring it all of the time, and so you're starting to see these common things. So what makes our code easier to work on, more maintainable, and have fewer of these red hot spots? What are the characteristics of that code in simpler terms that people should be shooting for, do you think?
So I think that writing good code is not so much about doing the right thing. It's about avoiding a lot of stuff. And one of the things you should definitely avoid is to have lots of conditionals, because each one of these conditionals, they basically represent a state, right, that you need to keep in your head. And in our head, we can keep maybe 3-4 things and actively reason about them, right? So what I like to see instead is that, take that part of the code, encapsulate it, put a good name on it, right? Now you don't have to care about those implementation details, and you can reason about the higher level concept instead. So then, of course, you have other trade-offs like that are super hard to come up with general rules for. Like the classic trade-off is, of course, you might have a tightly coupled system. You can break that coupling by duplicating code, right? And now you might have another problem. So there is always a trade-off, and it's very, very rarely that we can say that, okay, for this specific metric, it's always a problem to violate it, because it's easy to come up with counterexamples. So it's like, that's why we have under the hood at least 25, 26 factors, because code quality is so multifaceted that there's not a single metric that can capture all of it. We need to weight all these together. So it was a vague answer, but it is a tricky question to me.
But it reinforces a lot of my prejudices. My guess is that I would like your code if we were working on it together, from the way that you've described your code, because it sounds like very close to the way that I think about code as well. One more question. We're kind of coming up to time, I guess, but one more question. Does language make a difference? In your analyses of these different code, could you say that functional systems have less red code than OO systems, or C# is better than Java, or whatever else it is? Do you see those sorts of patterns in the things that you look at? Because we often, all of us as technologists, tend to get obsessed by these things.
It's a fun question. I actually have some data on that. I've never published it. I'm going to do it someday. But basically, let me try to answer it that way. That when I do a conference presentation and I want to illustrate certain code smells, right? Then I know what language to look at, because I like to think that, there are problems all across the language space, but I think the communities value different things, and that kind of tend to go in both directions, also, reinforce some code smells. So if I look for things like overly over-engineered, over-abstracted code, right? Leaky abstractions, then Java is a safe bet. If I look for overuse of mock libraries, right, where you have tests that basically test nothing but the mock library, then I go for C#. And if I want to find some really massive brain classes, then I know that C++, that's my go-to. C++ trending on GitHub.
Yeah,
there are different languages have different problems. That said, I think that in functional programming you have a massive advantage because you can write crappy code in functional programming too, but it's going to be so much easier to refactor that code without any side effects and mutations, right? So you are in a better place.
Interesting. Cool. It's been really interesting talking to you, Adam. So thanks again for agreeing to do this today. Let's just wrap up. Just to put words into your mouth, I'd summarize the way that you kind of talked about this is that code complexity isn't really the problem. It's the complexity of the hotspots, the places where the code changes that really matters. And that's what this approach, by combining the kind of the metadata and the quantitative measures of quality in the code, you get this insight, this visualization of this. Would you think that's a reasonable summary?
Yeah, it's a very good summary. I like that.
Good, thank you. Thank you very much indeed to everybody for watching. Thank you once again to Adam for sharing his expertise and his insights today. If you do remember to go and check out Equal Experts links, thanks to them once again for supporting us. And if you haven't come across us before, remember to subscribe. And if you enjoyed our conversation today, hit like as well. Thanks again, Adam, and bye-bye.
Thank you very much.